Hello everyone and welcome to this week's lecture. So last week we talked about linear regression and how to use linear regression in making prediction for continuous variables and also for making a classification. Today we'll be talking about non-parametric models. So as we saw, linear regression uses the training data to estimate a fixed set of parameters, and we call that vector W of weights. And this vector W essentially defined our hypothesis, which we called h of x. And at that point, essentially we can throw away the data because all the information that was carried by the data is now summarized by the weight vector W. Now, a learning model such as linear regression that summarizes data within a set of parameters of fixed size, because we know that the vector W has a fixed size, independent of the number of training examples we're working with. This is called a parametric model. Now, when data sets are small, it makes sense to have a strong restriction on the allowable hypotheses to avoid overfitting. Remember, overfitting happens when your model is just too complex given the amount of data you have to work with. But when there are millions or billions of data points to learn from, then it's probably a better idea to let the data decide rather than forcing them to fit a specific tiny vector of parameters W. So if the data say that the correct answer is a very complex function, then given the huge size of data, we're talking millions and billions, then there's no reason why to force it to simplify the model to a linear function or something even more constrained. So that's where non-parametric model comes from. So a non-parametric model is one that can't be characterized by a bounded set of parameters. So essentially, we don't know ahead of time how many parameters we're going to end up using to define the model, unlike for regression where we knew before doing anything how many components will be in the vector W. So learning methods that do this have also been described as instance-based learning or memory-based learning. The simplest instance-based learning method is essentially a table lookup, right? Because you take all the training examples, you put them in a lookup table, and then when you're asked to make a prediction for a given x, so h of x, you see if x is in the table. If it is, then you return the corresponding y. So that's really essentially there's nothing to fit here. There are no parameters to the model, and you're just looking up the data. Now, what happens when you don't find x in the table? So that's where the machine learning comes in. Okay, that's where we have to start making predictions. So the easiest idea then for a non-parametric model, if you can't find x in your table, is to find the nearest x, right? And use the value for y for that nearest x as your best guess as to y for the true x you're interested in. So that's a slight improvement over the lookup table. This is a method called nearest neighbor model, where given a query xq, instead of finding an example that is equal to xq, find k examples that are nearest to xq. So instead of just finding one point nearest neighbor, now we're going to find k nearest neighbor. So this is called the k nearest neighbors lookup. Okay, so we use the symbol NN, so nearest neighbor. K is the number of neighbors we extracted, and XQ is the query we're looking for. Okay, so for example, if K is 3, then in that case we're gonna pull the 3 nearest neighbor, and obviously you can predict right now that we're gonna have to define what we mean by nearest. Okay, how do you know that one training record is near the other record? How do we measure that distance? So that you will see that this has a big impact on the accuracy of these models that try to find a nearest neighbor. So let's say, for example, we pick k equals 3. So we're going to pick the 3 nearest neighbors. And then this is a classification problems between yes and no. Okay, or black and white, for example. And let's say out of these 3 neighbors, 2 of them had the classification yes, and 1 had the classification no. Then for our query that's not in the table, XQ, we will conclude that for XQ we will also be a yes, just because majority rule, and 2 out of 3 said yes, and these are 3 neighbors very similar to XQs, and we will say XQ is most probably yes. Okay, so what if we have a tie? Well, to avoid ties, we just typically pick an odd number of k's. Okay, so this way we don't have to worry about dealing with situations with a tie. So that's for classification. What about regression? Okay, so if we want to do regression, again, we're going to go and pull the 3 values, if k is 3, and pull the 3 values. Each value corresponds to one of the neighbors, and then we can just take the average of the 3 or take the median of the 3, depending which one works better for us, and then decide that this would be the most appropriate prediction for that query XQ that is not in our table. Okay, so if you look at the decision boundary here for k nearest neighbors, okay, for on the left we had k equal 1, and on the right we used k equal 5. Okay, so the boundaries are defined by that shaded area. So with k equal 1, you're gonna have a lot of classes, obviously, because essentially you're only looking for one neighbor. Okay, so with k equal 5, we get a much smoother boundary, which is this one on the right here, which has much less overfitting than what we had here. Okay, so in this case, this you can see that we overfit this area. That's probably not a good generalization. We also overfit this area right there. Okay, so as you can see, non-parametric methods are still subject to underfitting and overfitting, same as parametric methods. So in this case, we just saw the one nearest neighbor is overfitting because it reacts too much to the outliers, the one on top and the one on bottom. Using k equal 5, however, gives a much nicer looking boundary. If we go to a higher k, we might even underfit and end up with too simple of a boundary. So as usual, we can use cross-validation to tune the model and find the best k. Now let's go back to nearest. We said earlier that the word nearest implies that we're going to be using some distance metric. So how do we measure the distance from a query point xq to an example point xj that we have in our table? So typically distances are measured with what we call the LP norm, which is defined by this summation. So we take a summation over all the components of the vector x. Remember that x is a vector, right, with many features. So we take a summation over all the features of that x vector. We take the difference feature by feature. We subtract the given neighbor xj from xq, and then we take the p2. If we said p equal 2 for that equation, so we're taking the square root of the sum of the squared distances, and that gives us Euclidean distance measure. If instead we take p equal 1, then all we're doing is we're taking the sum of the absolute distances, because p here is 1, so the absolute is raised to exponent 1, and there's no root outside, and that's called the Manhattan distance. So these are the two really most common measures that we use to measure nearest in the context of k nearest neighbor. Now we could, if we have Boolean attributes, so attributes that are not continuous variables or integers even, they're Boolean, for example, black, white, yes, no, anything like that, then we can use the Hamming distance as the nearest neighbor measure in that case. So typically Euclidean distance is used if the dimensions are measuring similar properties. So for example, let's say you're trying to build a model to predict the price of a house, and your feature vector contains for example, number of bedrooms, number of bathrooms, number of cars in the garage. So they're all similar. In that case, they're all numbers of something. So in that case, we would use L2 Euclidean distance. Okay. Now, Manhattan distance is used if your features are not similar. For example, if you decide to instead use features such as the square footage of the house, number of bedrooms in the house, whether or not the house has a view. So features that are not similar. You can see here I give you examples of a continuous feature, which is square footage. I gave an example of an integer feature, which is number of bedrooms. And then an example of a Boolean feature, which is does it have a view, yes or no. So when you have a mix of feature types like this, then we use Manhattan distance in that case. Now, note that if we use the raw numbers from each feature dimension, then the total distance will be affected by change in units in any dimension. So if you just go back to this example here with square footage, number of bedrooms, number of bathrooms, square footage is in the thousands of feet, but number of bedrooms is 2, 3, 4. So if you just use the raw features like that without any normalization, square footage will have a much higher impact on the Manhattan distance. So to avoid this, we apply normalization first to the features, and then maybe by dividing each feature by the maximum possible value, for example. And then we can then use the normalized features to calculate a distance between the different data points. Okay, we continue in the next part.